All right. Thanks. So I will be talking about a private order book, but yeah, there is a general, a much more general topic that I would like to touch upon, which is really making things private, and in particular making DeFi protocols private. So I'm Damian Straszak, I'm with Aleph Zero, and let's jump into this. So you're all probably familiar with this picture, which is a graph of transactions on a public blockchain. And well, this is the very nature of blockchain, that everything here is visible, right? So you can look at one particular account, at one particular user, and see the whole history. See what this user has done, and what were the transfers it has done, what were all the transactions this user has ever committed to the chain. Which is really bad, right? Because we would like rather the transactions to be private. So how can we how can you solve this problem? So in fact, there are already known solutions to that. And as you probably have heard, they all use this famous moon math, right? The ZK snarks. So what I mean here are protocols akin to Zcash, Tornado Cash, and what we are working on Aleph Zero, the Shielder protocol. So why is it called the Shielder? It's because what we are doing here is often called shielding tokens. Okay, so we enter from the public space to some kind of a shielded space where the transactions are pretty much invisible. Okay, so I will not talk about technical things today too much. I just have one slide to explain you the main idea of the Shielder, of how this moon maths, how this snarks work. So here's the idea. Me, let's say address 1, would like to gain some privacy. So what I do is I send one ETH to the Shielder, which is, let's say, some kind of a contract on chain, and I attach a particular password to this transaction. Actually, not even the password, but the hash, so that the password is hidden. And then, in order to withdraw from the Shielder after some time, I just prove that I know some password of some particular deposit that has been done to the Shielder. Okay, so I don't point to a particular one because that would be kind of pointless. That would actually reveal that this was me who was depositing. The main point here is that the deposit and the withdrawal are not linkable. Okay, so no one is actually learning the password, and this is pretty much how it works. Although it's a little bit simplified, I have to say. So if you see some gaps, you see things that doesn't make sense here, that's valid. And yeah, this is only for simplicity. Actually, yeah, it's intentional. So all these issues here are kind of fixable, so don't worry. So ZK snarks, how are they used here? In general, what ZK snarks allow you to do is to generate proofs of statements of the form, given some private data X, the result of a computation F run on X is Y. Okay, Y is typically public in this kind of a setting. So here, the way it is used is to kind of prove ownership of a tokens because I know some kind of a private password. Okay, and again, this is a little bit simplified. In reality, it works a little bit differently, but yeah, this mental model is quite accurate actually. Right. So this was simple, right? So using these simple tricks like the ZK snarks, we managed to make token transfer system, which is really private, or at least kind of private. So, well, let's do something even better, right? Let's make the whole DeFi private, because that's what we would like to do. And, well, I think, yeah, I talked to many people, some of them technical, some of them not. But I feel like the general understanding, especially among non-experts, is that privacy is kind of a solved problem on blockchain. And there is actually even like a very specific recipe that you need to follow to make an app private. Okay, so here is the recipe that I am being told quite often. So you start with an app, and then you just pick your bullets, right? So there are many bullets in this box. These are called ZK snarks. There are Plonk, Nova, and so on. Like there are new bullets are coming pretty much every month, because this is an active research area. And you shoot the bullets at the app as long as it becomes ZK. Okay? So what I would like to say, and what you would probably realize quite early after spending much time on this, is that the story is not so simple. Actually, you will soon realize, after you start working on that many DeFi apps, they require to store a particular state in the contract. They have many different components that are not really comparable to token transfers, as we have seen before. So it's actually much harder to make them private. And it is like what I would like to convince you today, giving some kind of proofs, as you will see, is that snarks are very often not sufficient to make these things private. Okay, so you will need some more powerful technology, and these technologies are being developed, and we will surely use them to make some more sophisticated protocols, more sophisticated DeFi apps private. Okay, so let's see. The main example that I would like to discuss today is that of an decentralized exchange, so a DEX. And you can think of just, say, the basic design of Uniswap version 2. Okay, so you remember this is the constant product model, A times B equals C. We'll see it today in more detail. But yeah, this is just something to keep in mind when we go over the slides. Right. So let's see. What's the simplest way to make a DEX private? So here's the picture. Let's assume that there is a user who is using this shielder primitive, and the user is using the shielder to hold all its tokens. Okay, so this is actually how you are supposed to use the shielder. Maybe some of the users actually use this kind of protocols as some mixing tools where you just enter and then you withdraw at some point later. But yeah, actually I think like the best way to use them would be just to just hold all your coins. And if you make the user experience of that not too bad, then I think all users will kind of opt in for this way of storing coins, right? So suppose we have such a user, and this user is actually making a swap on a DEX. And this user is exchanging one ETH for, let's say, 1,800 DAI. Okay, so what is happening here really is that this DEX that we have on the picture is simply a public DEX. So this would be like a regular Uniswap contract, okay? Nothing fancy, nothing ZK for sure. And the only thing which has some like privacy, cryptography in this picture is the shielder thing. Okay? So the user is kind of withdrawing from the shielder, making the swap, and coming back to the shielder with a different token. So, one observation is that this is indeed giving some privacy, because now it is not clear which user actually did the swap. So this is good. But the issue is that, well, it is not 100% private, because we all see what trade is really happening. We are seeing that this transaction to the DEX, this contract call is really public. So yeah, the transaction details are not quite private here. Right. So what we come to is this kind of a table which gives us some kind of hierarchy on what could be the levels of privacy that we can get on blockchain, or we want to get on blockchain. So the basic level 0, let's say, of privacy on blockchains is pseudonymity. Okay, this is what we get by default because we just use accounts, right? Accounts are these like long hashes that we never remember. We just like copy paste them, and under such a hash, there is normally just one user who uses this account. And whenever a transaction happens, what you see on chain is just that like one hash send some number of coins to another hash. And this is not really revealing who the user is. It is not revealing what is the real name of the user behind a particular account. Of course, the issue here is that once someone makes this kind of a mapping, once someone kind of finds out who the user is behind this particular account, then it's pretty bad, because then you can actually backtrack the whole blockchain and see what kind of transactions this user made and essentially see the whole history. So this is what we would like to avoid. And yeah, this is what anonymity actually is. This is the level of privacy where each transaction is anonymous. So what we see on the chain is that someone is sending, let's say, one ETH to someone else, and we don't really see who someone is. Okay, so there are just like a bunch of such transactions, and you are always seeing someone, and like, of course, someone is a different person in each transaction, but you cannot link them together. You cannot link all the transactions of a single user. So this is level 1, and I would say the final level, the best, what you can get is the full privacy. And this would also hide the details of the transaction. Okay, so you would not see that someone is sending some tokens or someone is swapping some tokens. You would just see that something happened. Okay, but you have no idea what. Okay, you have no idea about the value of the transfer. You have no idea about anything. All right, so this is the best we can hope for. Great. So now we know what privacy is. We can actually try to get it, try to make things private. So again, we have seen a lot of progress in snarks, and a lot of people are excited about them, and rightfully so, because they are really powerful and they can give us a lot of things. But yeah, what I would like to say is that it's not that they are solving the whole problem of privacy. So one ideal solution for privacy would be the following. The problem of blockchain is that the state of the contract is public, right? So maybe let's just make the state private using snarks. Guys, why don't you do that? And well, here is a kind of an argument why this is hard, or this is not really possible. So what happens on chain when you make a transaction to a particular contract So imagine this is like this imaginary ZK contract, which has the state hidden using snarks, is that there is a state 1, the transaction happens, and the state changes to a state S2, right? So how can we kind of realize such a system, such a contract with a private state using snarks? Well, what we would need to do is to have a prover who will generate a snark that the transition that happened is actually correct. Of course, the issue here is that the states are kind of private, so we cannot even like prove things about them, only about their hashes or something like that, but like that's not the problem here. The problem is always that in order for someone to prove that a given state transition is correct, they need to know the data. They need to know the states. Okay, so the prover would need to know both the starting state and the final state, of course, the transaction as well. And the question then becomes, well, so who is supposed to be the prover? Alice, the transaction, who made the transaction, is certainly not able to do that. And whoever would be able to do that would need to know the state. But the state should be hidden. The state should be private. So like this is some kind of a contradiction, right? We cannot really do that. So one could ask, wait, so you are saying this is not possible, but we just saw that for token transfers, this worked, right? So we could make a private system, or at least an anonymous system, using snarks. So there is a particular reason why this worked. The reason was that Alice, or whoever made the transaction, knew enough about the state of the contract to actually generate this proof of transition. Okay, and this enough was essentially the balance of Alice. Okay, the balance for a particular token of Alice, because if she is, let's say, sending some tokens, then she can generate a particular proof about this, about just this part of the state, and this is enough. Okay, so this is like some kind of a generic argument why doing things using snarks is not so easy. But it's okay. You might not believe it because it is generic. It is like very, very little detail. So I will give you an even more general argument saying that actually no matter what you use, you will not get private states. Okay? And by no matter what you use, I mean you can use MPC, you can use homomorphic encryption, you can even use a trusted hardware. Okay? And well, how do you prove it? So here is the thing. Suppose like this transformation was possible, that we can start from an app and just make it ZK. Then, well, there is a simple kind of strategy for the adversary to kind of infer what the state is. So the adversary will just like throw a bunch of transactions on the contract and look at the results, right? Basically, using this strategy, you can read a big chunk of the state by just like seeing what the results of the transactions are. So this is still very generic. So I will like look at this particular example to convince you that this argument is actually valid. So using so we can look at the example of the AMM DEX, the Uniswap with a constant product rule. So yeah, I will go very quickly about it, but what you can do is by sending just 3 transactions, actually 3 swaps, you can actually derive all the variables inside of the state. Okay, so no matter how are they hidden, you will be able to actually get them, right? So private state is not something we can get, no matter what the technology behind it is. So yeah, this is quite sad and kind of disappointing, but it's actually not so bad, because one can also realize that maybe it's not the private state that we care about. And the second thing is that Well, there are many different designs of DEXs, so maybe AMM is not the way to go for privacy. There are order books as well. And yeah, all of this is accurate. And I think like one important rule for designing private dApps would be to actually first define the problem properly. Okay, so we need to say what do we really want to make private for our solution first. This is like a fundamental step to make. And in particular for a DEX, what you could probably want is to say I want anonymity, like this is a basic thing. I want some kind of a property that the moment the trades are kind of revealed is the latest possible, meaning that we get some kind of a front-running protection. So this is like a very nice property that that privacy would give you, right? And well, there are some other things that we would like. Probably limit orders would be nice. Like this is something that you don't get in vanilla AMMs. So these are all nice properties that we kind of demand from a good private DEX. And well, here is what we are working on in Aleph Zero. We work on Common, which is an order book which has privacy. So I guess I'm running kind of out of time, so I will not really read out this slide. I will just go to the example, which explains it quite well, I think. And the way the system works is roughly as follows. So as a user, you hold your tokens in the shielder. And if you want to make an order in the DEX, you just send a particular transactions which registers an order at a particular price, at a particular direction, buy or sell, and it has the amount of the order hidden. Okay, so this amount is encrypted, it is not public. So what happens periodically, let's say every 10 minutes, but this is something to configure, we gather all the buy and sell orders that kind of match the current market price. We aggregate them together, and then what happens is that the aggregated values on both sides, buy and sell, are revealed. Okay, so what do I mean here by revealing these values? So this is actually the part of the system which is not using snarks. So this is the part of the system where snarks would be kind of not sufficient. Okay, so for this we need like a weak form of multi-party computation. So this is like, you know, a pinch of salt, a pinch of non-snarks that we kind of need here. And actually I would argue every private system for like a kind of a more complex DeFi product needs. And yeah, so this is a weak MPC primitive, which is just collaboratively decrypting some kind of a value. Okay, so then we get this value in the public. We do some internal matching between these two aggregated trades or orders, and then whatever is left is traded using a Dutch auction in public. Okay, so this is kind of the complete mechanism. The Dutch auction, importantly, is like completely open, so nothing private is happening there anymore. It's just open for market makers to just offer whatever trades they want, as long as they're fair. And yeah, after this resolves, all tokens are put back into the shielder. Okay, so that whatever happens in the trade, user essentially claim privately the trade results from shielder to the shielder. So nothing is really leaked about the values or other details. So yeah, this is what I just said. We don't reveal particular orders. We can also obfuscate the order book by sending some, small orders or zero orders, because like this is the way to kind of beat the problem that you need to specify the price. But it's just the price, right? So if the amount under the order is hidden, it doesn't tell you much, especially if we like flood the order book with like fake small orders. So then the aggregation kind of hides all individual orders. So this is the Dutch auction. So I will kind of skip through it because I'm running out of time. But this is quite standard. It's just for economic efficiency of the DEX. And basically then all the results of the internal matching and the Dutch auctions are combined, and the user can claim the traded tokens. So just to conclude, the general message is that making private dApps is not so simple, and I think it's very case specific. So you really need to think about your dApp. You really need to think what are the properties that you would like to get from the privacy, and only then you can actually try thinking how to actually achieve that, whether snarks are enough, maybe you need some kind of stronger technology. And regarding Common, a big shout out to Nethermind. The team from Nethermind has been working with us on the design of Common, and it's been very fruitful. So we think that, this will be a private protocol that doesn't compromise on the UX, and it's generally something that is both kind of good from the economic perspective, and it should be kind of user friendly. So this was our goal. Thanks.
Thank you, Damian.